Today we have Jack Atkinson from the ICCS RSE team, who will be conducting the RSE skills course and showing us how to write proper, better research code and make it more readable and nicer. And hopefully this will be a skill that you guys will be finding useful. Jack has been here at the University of Cambridge for quite a long time and is now at the Institute for Climate Computing, or Computing for Climate Science, and has a lot of expertise in geoscience and geology, and has been working in the geology department and the engineering department here. And he will be conducting the session today. So give it up for Jack.
Ooh, thank you, Gajit. Hopefully people can hear that and it's coming through. I'm here to talk to you a little bit about kind of writing better code, but not particularly writing the code itself, but also kind of cool tools and techniques around the software rather than the code that hopefully can help in your work. And this is sort of subtitled in Python because that's what I'll be using to do most of the examples, but I'll try and provide pointers to other languages where appropriate for people to follow with, and I guess get started. So as a couple of precursors, so the materials for this workshop are on a GitHub repository, which is on a link here. You can find that going to my GitHub here. Sadly, I can't share a link because we're not on Zoom. But if you go to there, that's the GitHub repository. If you go from there, you can find a copy of the slides at this link, so you can follow along in your own time, and also click on any of the links that might come up there. And I think Gurjit also sent an email around with this link in yesterday. As a couple of sort of precursors to that, hopefully everyone can be nice. If you've got a question, please just stick your hand up. It's better to discuss it as we're working through some things. And there will be some mistakes, and not all of them will be intentional. So if you spot something, again, please give us a shout. And then, yes, like I say, there's sort of the way this is going to work is I will talk through some things. There's then some practical examples that I will do demoing on here. You can follow along on your laptops. Because we're sort of compressed in time today, we probably won't go in detail through everything, but the exercises are structured such that you can come back and finish them sort of in your own time after this playing around, and all the materials up and online. So the idea is we're going to talk a little bit about sort of why good software principles matter when you're doing research. But in particular, this is, like I say, this is a practical course, so it's sort of how you can apply these things when you're writing your code in your everyday research, particularly kind of core principles to follow, some key tools that will make your life easier in doing this, and useful techniques around that. So specifically, and if you don't know these things, we'll come on to talk about them in more detail anyway, but we're going to go through kind of user environments as a starting point. We'll then talk about kind of some best practices in formatting and linting. If that looks like a weird word to you, it was also a weird word to me before I started working in RSE. And then we'll talk about sort of some general principles when you're actually writing the code for making things a bit nicer. So the first thing to do, I would say, before we start talking is if you haven't already got a copy of the code, please do so. Those who might not be as familiar with GitHub, if you go to the code button, click the HTTPS, or SSH if you know what you're doing, but otherwise the HTTPS, copy this URL, and then if we go into a terminal, we can run git clone, paste that URL there, and it will pull everything down, and we can then navigate into that workshop there, which hopefully, yes. So yeah, I would start doing that if you haven't already, and whilst you're doing so, I will continue talking a little bit. So for a start is sort of the question of what is research software, and I've got on the right hand of the screen here sort of the epithet of the Software Sustainability Institute, which is that if you've got better software when you're writing things, it will, in the long term, enable you to do better research. So Part of that, I think, is when we think of research software, we think of sort of major computational programs. So where I work, that would be large-scale climate models. Other people have maybe got galaxy simulations or cosmology data here. But it's also kind of the data processing. We write a lot of software to look after that. And it's also experiment support. So we have kind of a lot of observations that are going on, sort of if we're talking ocean or atmosphere, from stations there, or you've got observatory data, things like the SKA generating huge amounts of data, sort of petabytes, that has to be handled by sort of clever software. So research software sort of covers a huge range of things. As for why this matters, so there's sort of the apocryphal story, which I'll let you read in your own time, but essentially there was a researcher who was on a high-flying track, Nature publications, yada, 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 and then someone tried to reproduce their sort of seminal paper and found that none of it worked. And it turned out they'd had an Excel sheet where they'd reversed the indices and everything that they'd built their career off sort of collapsed. So that's the horror story to make you wonder or think why you should care. But just this morning, there was a project I was working on where someone had it was a large CFD simulation. They thought they were sort of taking a slice below 30 kilometers. It turned out what they were doing in their code was taking a slice of the bottom 30 indices. And you can imagine if you'd got sort of 3 or 4 times the mesh resolution, this is going to give drastically different results, and it's something they hadn't spotted. So this is one reason it's important. But I think more important long term and sort of beyond papers is we all kind of want our code and our research to do something. And your code may one day find its way onto a satellite, sort of into policy decision making, and you want to be sure that sort of to the best of your ability you can trust what you've written. One example of this being, I guess, does anyone know who that is? Forgot her name. So it's Margaret Hamilton, who wrote the code that or led the team writing the code that did the first sort of moon landing. And there, yeah, it was very important that the code was correct. And the reason she's up here is that she was arguably the first person to coin the term software engineering in practice. So yeah, more practically sort of why does it matter? Can anyone tell me briefly, I'll give you a minute, less than a minute, what this code does? Yes? Yes. This is always more fun when I ask humanities people in this course. But so exactly the same code, but is it maybe easier if I ask you what this code does? Cool. So if you spend the time comparing the two, the code itself is identical between the two, but you can see there's a lot of things that make it a lot more readable so we can interpret, but there's also a lot of things going on that make it much easier to sort of understand when you come back to this code, maybe in 6 months' time, how it's working and what it's doing. And this is the kind of thing the course today is aiming at, is sort of how do we achieve this with the minimal effort. So the first thing we're going to start with is virtual environments. And as I say at the start, sort of there will be probably some things here that people have covered before, probably some things that haven't. Hopefully you will go away learning something at the end of the day. If not, sorry. So just as this is always an interesting one, so as a quick show of hands, how many people do use virtual environments in their work? Okay, that's quite cool. And how many of them is since Ubuntu started making you use virtual environments? At least one person in the back. Cool. So most people are familiar, so I'll go through relatively speedily, but the idea of virtual environments is if you haven't been using these and you start using some Python code and the Python says, oh, you need NumPy to run this, you would sort of do pip install NumPy. This would dump NumPy somewhere onto your computer and then you could use it. What happened recently was that NumPy moved to version 2, which meant that a load of things broke in version 1 and they sort of weren't backwards compatible. If you had just pip installed NumPy and you updated it, this meant that any code that used the new NumPy worked, but any code that was still relying on the old NumPy suddenly stopped working, and you sort of had to pick, well, do I want the new one that makes this code work, or do I want the old one that makes this code work? Virtual environments, or more generally kind of software environments, solve this problem by saying, let's construct kind of a separate box where I put all the software needed to run this particular piece of code. When I finish doing that, I sort of close that box up. I have another piece of code. I create a new box with all the requirements that are needed for that. And that way there's sort of no cross-contamination, and I can be very, very sure what I'm running with. So in Python, which is what we'll be talking about, Python achieves this by essentially creating a separate folder where it places all of your dependencies. And when you are working on a particular project, you tell Python, use any of the packages I've installed in this folder. When you stop working on that project, you can then go and point at a different folder, install other things there, but you can always come back to the folder you previously created. So yeah, like I say, the idea is to kind of avoid polluting your system with lots and lots of different versions of the same thing, also allow you to use different versions on different projects. And if you're interested in kind of reproducibility, you can actually get very, very specific and say exactly which version of a package your software works with when you hand it over to other people. How do we do this? So Python comes with inbuilt tools for managing this. There are also a number of kind of third-party packages, which I'll talk about in a moment, but the most sort of simple, straightforward one that will be on everyone's system is the Python venv, or Python virtual environment. So on Linux, the way we do this is by running this command here. This is saying use the Python 3 that's installed on my system, create a virtual environment, and then the final argument here is the name of the virtual environment here. You'll often see, if you're looking at documentation on this, people will just call it venv or .venv. My advice is to try and give it a slightly more meaningful name, so that if you are working with multiple environments, you can come back to it and remember which one is which. So over here, you will see that I've cloned the repository and I've got the documents there. So the thing we're going to do is run Python 3 -n venv, and then I'll call it RSE skills. And after it's had a moment thinking, you'll see that it's created the RSE skills as a folder there. And if we sort of look under it, you can see there's a few binaries and libraries that's where it's going to dump everything we install. However, we're not sort of safe yet. We've created that environment, but we're not inside it. To do this, there's a script inside that we have to source. So if we do run that, we do source RSE skills bin activate. And you'll see that once we've done that, a handy little thing has popped up by the side, telling us that we are now inside a virtual environment, and specifically which virtual environment we are inside. And you'll see what we can now do is install anything we want, and it'll go into here. So if I go pip install numpy, or maybe I should do something slightly more esoteric, but you can see we've installed numpy 2.3.5. If I now do deactivate, which is the command to close that virtual environment, you'll see that the precursor to our prompt here has disappeared, telling us we're no longer in that environment. And possibly if I run Python and try, and I have a horrible feeling, no, perfect. So you can see I have pip installed numpy in the environment, but from outside the environment, I can't see numpy. If I were to go back into that environment and now try again, there we go, numpy's there. So we've created this nice barrier and compartmentalized everything. And I think that's just demonstrated. The final point I'd like to make here is that we deactivated the environment, went to do something else, came back, and everything we had installed was already there. And this is true of both packages you get from PyPy, but also if you've pip installed your own code from the command line, this will also be put into here. Cool. So, and the last thing is if you have done something horrible, you've sort of balked everything, got environment clashes, You can start from a completely blank slate just by removing that directory that was created and starting again. So, are there any questions on that? Yes?
This might be a stupid question, but
Not at all.
if you had a conda environment and you also made a Python environment, do you know what would happen? Or, I'm assuming you shouldn't do that.
So, this brings me on to the next slide, which is, we've talked about Python. There are other systems in other languages, because this is a good idea. There are also multiple systems in Python. So some people prefer to work in conda, which has a different approach to doing this, but carries out the same idea. Conda requires a bit more work to make code installable, and not everything that's pip installable is conda installable. When that's the case, the recommendation is usually just to use pip from inside conda. If you create a virtual environment inside conda, I don't know what would happen, but my advice would be not to do that, because if you pip install into a conda environment, you're putting it into the conda environment, and if something did go wrong, you could just get rid of that conda environment and create a new one in the same way you would do with the Python venvs. Then, yeah, other languages, sort of, you're in C++ or Fortran. I don't know, is astrophysics still in Fortran? All of climate is. Fortran's good. So if you've been using CSD3, you kind of have you're forced to use the environment system there by loading different modules through what's called SPAC, but you can also do that on your own computer. Rust, they've got cargo. Julia's got package environments. R has got renv. Now that you know what to search for, you can probably go and find some stuff. So that brings us to kind of the first exercise we've got, and we are doing astrophysics. So the idea is that you've got some data, you want to do some stuff, and your colleague has kindly given you some code that will do this, so you don't have to do all of the legwork yourself. The challenge, however, is that this might not be the most ideal code to work with for some of the reasons we've already mentioned. The first task is to create and load a virtual environment. So I'd suggest doing this kind of from the root of the repository. And then we're going to go to the code and try and run some of the things. So I'll walk through that with you here. So does anyone need me to go through? Yes?
I have a question that you're listening to what you said. Normally when you are cloning up a big repository from collaboration, is it better to install the environment within that repository or do all of this separately?
So it's a good question. If you know that you're going to be working entirely within that repository, then put it inside the repository. However, if it's going to contain lots of dependencies that you perhaps want to work with multiple different codes in multiple different places, then you could have a separate location with your virtual environments and sort of boot into those before you then go to that code. And that is sort of how Conda works, in that Conda stores all your environments in a special Conda place, and when you do Conda activate, it fetches them from there. It depends what fits best with your project. So we've created our virtual environment, and then what we want to do for the exercises is go into the exercises folder and go into exercise 1, which is kind of our base code. And in there you'll see there's a sort of the code I normally use when teaching this, which is the geoscience one. But we also, thanks to Gurjit and...
Thanks to
super. Okay, I will precursor this by saying I took your code and I made it purposefully worse. And that took a lot of effort because it was not bad code. So a lot of what you will see is me purposefully trying to make things bad. And thank you very much for doing this, because it gives you sort of slightly more relevant code. So there is the Astro exercise there. And if we open that up in a text editor, you will, we'll also need to go, sorry, to, now I've gonna, exercises 1. Super. So you will see some code there. Have a quick scan through it and see if you can make much sense of it. And then give it a go at running it from the command line in your virtual environment. And we will do that by running Python. And once another thing that's worth pointing out, just as a side note, is often now on Ubuntu and Mac, you have to use Python 3 when you want to run Python. Once you've created a virtual environment, because it specifies the version of Python to be the Python 3 you created that environment with, you can sort of drop the 3 from the front. You can keep it, but you can also drop it. So we will do Python and then astro.py, and it gets sad because we don't have matplotlib. So what we can do now is we know that if we do pip install matplotlib, this is fairly safe to do because it's just going to go in our environment. There's no danger of balking anything on our system. And now we can go and run our code. Except we can't. So the first thing that I would sort of really want you to take away after using virtual environments is that when you provide some code to do something, it's not enough sort of for a usability point just to provide the code. Does anyone have any suggestions for how we might solve this problem of sort of shotgunning and installing, shotgunning, installing? Someone had a hand up? Yes, perfect. Indeed. So all of those things that we're sort of missing, you can stick in a requirements.txt file. And the idea is it lists sort of all of those things that you would have pip installed, but allows you to do it in one fell swoop so that your environment is, if people do this before they start trying to run your code, everything is ready, your code should just run. It also gives you some additional things. So we talked a little bit about making your work kind of reproducible. So as well as listing those, can I do it from here? So as well as listing kind of things that you need, you are also able to specify versions. So we mentioned before kind of the NumPy, the great NumPy update. If you need to fix NumPy to something below version 2, you can specify that here. And if you really, really need to pin to an exact version, you can do it with sort of the syntax here. And the idea is that you provide something and people use this to install the code. If you install something new, then you should add this to the requirements file to make sure that people fetch it. One way, if I look at this, you'll see that in the root directory of the repository, we have the requirements.txt, and that's, it's just got a list of all the things we need to run this code. And the way we install that all at once is we do, as we would, pip install -r means just recursively use all of that file, and it'll go through and pull everything. This is probably going to take a little while, so I'll let that go away and do things whilst we continue talking. This is kind of the most basic way to do this, and it's what I'd suggest kind of you get started with if you don't have anything. If you want to learn a little bit more, then the term to search is packaging, and there's the sort of ways you can do this that will either pin all the versions very specifically or will make sure that your requirements is updated every time you pip install something. It gets more technical, but there's more to set up, so I'd suggest starting with this and providing this with your code as kind of the bare minimum. Okay, so exercise 1 sort of revisited is to go and pip install all of those things from the requirements, have a go at running the code, and see if it does what you thought it was going to do, which we can have a look at on here. Now that I have pip installed everything, hopefully we now run the code. It thinks about some things. Whew, and it's run. Anyone got any quick suggestions over what they think it's going to do? So in the interest of time, it's plotted two things. One is a set of velocities compared to survey data from a predefined data set. The other one is it's plotted a Hertzsprung-Russell diagram, or at least this is what your nice code told me it was. The last time I looked at a Hertzsprung-Russell diagram, it didn't quite look like this. I'm used to the one that sort of has nice pictures of stars and going down. But yeah, so these are the two things it's output. And the code that sort of as we work on this, we're not going to be changing any of the functionality of the code. We're just going to be changing sort of what it looks like. Okay, so any questions at that point? And I realize we're going quite fast through this, but the instructions are all online. So if you want to follow this through sort of after this, please do. Okay, super. So the next thing we're going to talk about is where things get a little bit more fun, which is PEP8 and formatting of code. So has anyone heard of the Python enhancement proposals? Okay, only one person, so we're getting better now. Hopefully people will learn some things. So the Python enhancement proposals are for members of the Python community to take things to the moderators of Python to say this would be a great thing to add as either a new tool to the language or a new specification or as just a best practice. And PEP8 specifically deals with formatting of code, which is how code should be laid out to maximize its readability and understandability, which is what Teller. There's a couple of other things that are maybe worth being aware of. I mentioned briefly kind of packaging. This was sort of something Python fell behind on for quite a while, but if you want to know more about sort of how to package your code better than a requirements file, PEP621 is the one you're after. And we'll come back to also the docstring conventions later in the workshop. But the one for us is the Python style guide, which is PEP8. Rats, bear with me. Maybe it's, there we go. Okay, cool. Cool, apologies. So PEP8, the full documentation is online here, and you'll see that it consists of a bunch of sort of recommendations for how you should be laying out your code to make it more understandable and more readable. For example, we can pick one here, which is to do with indentation, and it's suggesting you should use 4 spaces to indent things. So here they're saying if you've got arguments to a function that are spread sort of across multiple lines, you shouldn't put these all immediately under the function because it becomes difficult to distinguish what's the name of my function versus what are the arguments I provide. Instead, you should use 4 spaces and indent them like this, so we can see this thing here is the function name. Anything that's further indented are the arguments I pass to my function. Seems sensible. Where else is there? A whole bunch of things. Something about line breaks. What do we have? Line breaks. Okay, here we are. So you've got something, again, spread across multiple lines. Do you put your operators at the end of the line, or do you put them at the start? You could probably debate either way. PEP8 is sort of making a definitive decision for you, saying we think it's clearer if you can see what the operation is for the thing that follows it. Piles and piles and piles of this stuff. And you may be sort of looking at this thinking, this is great for software engineering, but how the hell is anyone meant to remember all of this and make sure all of this is in their code? The good thing, like I said, is we want the laziest approach, and the good news is that you don't have to. So, So here's a bunch of things that is a reason why we want to adopt good formatting. And this sort of follows from, if you've never seen the Python Easter egg, if you boot into Python, I think, do import this, you get a nice little poem about how Python code should look. And the important bit I'm focusing on here is that readability counts. So being able to give someone some code, it being in a standardized format that's easy to read, is important. So yeah, if you don't have time to memorize this, the good news is you don't have to. There are tools that are out there that will automatically take your code, however you've written it, and force it into a compliant style. Sort of they come with their own opinions that conform to this or beyond, so that you don't have to worry about what the best thing is. The one we're going to look at today is called Rough. There are others out there, but kind of this is a tool that you can just run over your files and it will automatically edit them. So the way we can get it is through pip. So it's all available online. We can use pip install and it will pull it in. Let's bring that back there. Here's the rough. It will go away and do some things. And then the way you can sort of force it is by doing rough format, saying I want to format a file into a compliant setup, and then you provide it with the name of the file you want it to do. Now, before anyone clicks enter, be aware that this will automatically overwrite the file with compliant, so just be aware of that. I believe if you don't want to do that, there are... okay, I've done that. What I want to say is if you do rough format and look at the help, it will show you that there are options to sort of do a dry run. So it will tell you to the terminal if it's going to do something before you choose to do it. Not part of this workshop, but hopefully all of your code is on version control. So if you did happen to overwrite a file, you can, of course, just roll back to a previous commit. That said, the important thing to note about Rough is that it won't change any of the functionality of your code. So all it's going to change is how your code is laid out and sort of bits of white space. It's not going to sort of say, oh, I think your for loop would be better implemented as matrix calculation, let's do that. All of the behavior would be preserved. So it's not the end of the world if you run this. And as you saw, if we run rough format, it will go over and modify those files in place. So probably if I go back over here and reload that file, you can see it's reshuffled a whole bunch of things to make them more legible. For example, we've got sort of these arguments are nicely laid out. They're indented by 4. The operator comes before them. All of those things. What else we got? Double quotes. One of the things enforce is using double quotes in strings. There's a whole bunch of things, but this is a tool that will automatically make sure your file is compliant to this standard. And you can run it on a single file, but you can also run it on an entire directory. So sometimes what's fun if you're trying this for the first time, run it on a directory of 50 however many Python files, and sort of you'll see that they're all updated. So I think there's just an example here of, on the left is what the code might have looked like at one point, on the right is what the code looks like after you run the formatter over it. So you can see it helps with things like, what are the arguments to my function, where are they, I can't tell sort of how many there are, where they are, Now they're all nicely listed here. Similarly with sort of white space, we've got this kind of standardized spacing of statements. I will say sort of the first time I started using these tools, some of the things looked slightly odd. So I'd been used in some of my research code to spending hours making sure all of my function arguments were sort of nicely lined up, only so many on one line. I came to look at this and sort of thought, why on earth are we using one line for each thing? The more you use this, the more you get used to reading this standardized format, and over the time, actually sort of your brain just comes to look at it as more legible. So there's a slight warning there. So any questions on that sort of as a general thing? Oh, cool. So sort of a few addendums to that is you can also run this tool on Jupyter Notebooks. There's a little bit of configuration in there. And you can also configure it with some config files. So as I said, it is opinionated, but if you do want to change things like maybe the maximum line length or sort of the quotes you're using, it is possible to do that to suit your own preferences if you really want to. But my suggestion would be to sort of try and incorporate this into your Python coding now, because it does match this widely used standard, and there's a lot of plugins available that will apply this. And also, if you're using things like continuous integration or pre-commit hooks on your code, if not, don't worry. But if you are, then there are abilities to sort of enforce this before you push up to your Git repository. And I can talk about that later if anyone has questions. And then, as promised, sort of other languages, again, there are multiple tools that exist in Python. If you're using C or C++, there's a tool called Clang Format. Fortran there's a sort of relatively new tool that does this based on Ruf, but is called Fortitude. Rust, I think Rust format comes as inbuilt when you install it. Julia has things, R has things. Your preferred language probably also has a thing. So exercise 2 is to try applying this to our code, which we've already done here. I have done that in the wrong directory, so I should say the structure of this course, because we're moving pretty fast, is if you look in the exercises directory, you'll see that there's a separate file for each exercise, and the file in each of those directories, you will find an astro.py file. The astro.py file in that directory is always the solution to the previous exercise. So if you fall behind, don't worry, just go into the next directory and you can come back and do this later. Yeah, the exercise is to install Ruf, pip install Ruf, apply it to the code in directory number 2, and have a look to see if you feel that it's made the code a little bit more legible. In the interest of time, I will let you do that sort of at your leisure. One thing that you might like to do is compare the files with sort of a diff. So if we are on the command line, we can do vim diff, which will show us kind of a side-by-side comparison. So we can do the exercise in the first, so you compare, the code in the sort of the base code we started with, and then the code in exercise 2 after you've run the formatter. And if we sort of look side by side, we can see a few things that have gone on. So here we've got all of these arguments sort of spread across single lines instead of stacked up. What else have we got? Sort of a long line has been condensed to fit on the screen. A few things here, we've got sort of operators stacked up here. You can look at this in your own time. That's the general idea. Okay, so as I said, applying the formatter will change the spacing of your code and the way it's laid out, but it's not going to change anything that might affect how it runs, even though there are ways that you could improve that as well. Fortunately, there are also tools that will help you with this, and this is what we call kind of static analysis. So to explain sort of the nomenclature there a little bit, static analysis essentially means we take your code and we don't run it, we just look at the source code, so it's static, not running, and we do some analysis and give you sort of some feedback at the end. So like I say, this goes sort of slightly beyond that PEP8 formatting to actually look at kind of the quality of your code, some of the maybe the security around it, and make sure that it's sort of following best coding practices. Other than writing better code, there is a useful reason for doing this, which is that it's not completely foolproof, but it will check for a lot of common errors that might be runtime. So the worst thing you want is to analyze your 3 terabyte data set, set your code running for 3 hours, it gets all the way through, and then sort of gets to the end and says, oh, variable not found, you put in a 1 instead of an L, and then you've sort of lost that entire run. By running static analysis, it would have said, oh, we think you've made a typo in the name of this variable, maybe you want to correct that before you submit your 3-hour job on CSD3. Again, sort of, this is not an endorsement. There's various tools available. We are going to use rough because it's nice that it provides functionality for both formatting and static analysis, and it is arguably the leader in kind of these tools. I'm not paid to say that, so it's okay. And the tool that we use to do this is rough check. So previously we used rough format, now we're going to use rough check. Before we go on to that, I'll give you sort of an example of what happens. So can anyone spot any issues with this code? Yes?
If param 1 and param 6 are like different, like if param 1 ends up being a float, you're gonna get an error.
So you're probably not, because Python does what we call duck typing, which is if it quacks like a duck, it's a duck. So it will promote it. But nice try. If this was C++, yes. Yeah.
Parent 2 is called parent with the numeral versus the letter 2.
Yes. So that's one. I think I maybe put more in, but I can't remember. Anyway, if we run the static analysis tool over our code, the output will look something like this. That's maybe a little bit small, apologies. But you can see it's caught a few things. So the important one, which you've just picked up there, is that we've got this undefined name param numeral 2, which is pointing out to us, yeah, exactly as you said, we've called it param TWO. And so if we get all the way down here, it's not going to know what to do. This is an undefined name. A couple of other things it's done for us that are quite nice. One is pointing out that probably in a previous iteration of the code, we had param 1, was it param 1? No, param 3. Param 3. So param 3 is still being fed into this function, but actually we've updated the interior so that it's no longer used to do anything. And so it's telling us that really you've forgotten to clean up after yourself, and you should probably get rid of this. Makes your code sort of more concise, more readable. The other fun one is this. Anyone know what this error is hinting at? Yes? Yes, so it is, no, it's not. So the nice thing about the output format is that it's telling us which file the problem's in. So this is the name of this file. It's then telling us it's on line 4, param 2, and it's telling us that character 15, which I think is probably there. So it's something, a problem with using this sort of this list. The nice thing about rough is it then gives you this kind of error code. So if it's not immediately obvious to you from the short explanation, you can take this error code and go and find out what the problem is. So one is by typing in the rule on the command line. So if we do, I'm going to slow down and do this correctly. So now we're moving to exercise number 3. So if I go in here, if we do rough check astro.py, you can see it gives us all of this feedback, but we know that it was B006 was the issue, so we can also do rough rule B006, and it will give us a little explanation of what the problem is there. You can also Google these error codes, so rough has a whole bunch of documentation that will give you an explanation. So in this particular case, the problem is if you pass a mutable argument. So a mutable argument is one that can be changed. So a list, you can append to a list, you can delete from a list. Passing this into a function as a sort of as a default, so we've passed in sort of this empty list as a default, is dangerous because it can give us unexpected behavior. So the example they give here, oh, there used to be a fun one with penguins. Oh well. The example they give here is that if you have a file that takes an empty list and then as that part of that function you append to it, the next time you call that function, you might expect it to append something to an empty list again, but it doesn't. Python will track that list in memory, so actually you'll be extending that original list every time. So the nice thing about the static analysis is it's pointed out to us that this is not a great idea and we should probably do something better. And the solution to doing this, if you want it to always be an empty list when you call this function, is to make this parameter none. And then in the code here, you would say, if param2 equal none, param2 equal empty list. And that way, every time you run the function, it will be an empty list. But that's a slight diversion. So the other thing to mention is that there's really good integration of these tools with your development environments. So if you're on VS Code, there's kind of a rough plugin for VS Code. If you're using sort of Vim, there's a plugin for Vim. If you're using Emacs, there's probably one for that. And I'll just show you briefly sort of what this looks like. So it's not in the environment I'm using for teaching, but if I switch to kind of the main environment I use for doing code, which is going to look slightly different, but bear with me. So if we now go into that direction with 3, if we now open up that astro.py file, so I know why that's not happened. So you have to have rough in your virtual environment, which will be in, sorry. Oh no, that was the name of our environment. Okay, sorry. Right. Haha, there we go. So if you integrate this with your editor, rather than relying on running the code after you've written it, or running rough after you've written your code, it will actually give you sort of direct analysis as you're writing things, and put it somewhere in there, sort of squiggly underlines or something. This is really, really useful, and I really recommend doing this because it kind of allows you to catch these things before. But the other thing I found when I started using this was that by having it shout at you in the text editor and you immediately fix it, over time you'll just realize what the errors are, what the common pitfalls are, and you'll start writing better code naturally. So yeah, there's a whole bunch of things here. We can see that we've imported AstroPy units, but we're no longer using it in our code. If we go down, here's an unused variable. Here we go, we're passing in a default mutable argument, our old friend B006. Yeah, it would give us a bunch of things. So I would strongly recommend sort of bringing this into your code editors if you can, and there's usually good documentation on this online. So if we go back, and I'll come out of that. Okay, any questions on some of that stuff? No? So again, other languages, if you've got something else, someone has built similar tools there. C++ and Clang, I mentioned Clang format earlier. You've also got Clang tidy. And there is also a tool, I think, CPP check you can do, which will bundle both Clang format and Clang tidy together. Other things you've got, yeah, you can go and find these. You now know what to search for. So exercise 3 is sort of going and running this on the code as we went through here, and trying to fix some of the issues that it throws at you. Does anyone sort of want to go through that now, or should we move on and you can have a look at this in your own time? Getting nods, super. So a couple of things, yeah, there's a couple of extensions. There is a thing, if there's something that's trivial to fix, so we saw the example of unused variables, or kind of sorting your imports. If it's something that can be fixed without changing how your code runs, you can give a -- fix flag, and it will do this automatically and overwrite the file. Some things that can't be automatically fixed without kind of your oversight, you have to get involved and do yourself, I'm afraid. Super. So I mentioned that you can configure what Rough is doing to your particular tastes. and this is done with a config file in your in the root directory of your repository. I'm going to briefly talk about that because it is useful for subsequent exercises. So if we, where are we? You'll see that this rough.toml file here, which is what provides the configuration. So if we open that up, you'll see that there's a few different things in here. So I mentioned we can change the the default line length, but the main thing I want to talk about at this point is kind of the configuration for the linter here. So the way Rough works is it organizes the rules it's going to apply on your code into a number of different subsets. So there's one here, which is pylint, which is general linting things. We've got E and W, which are white space. So this is going to deal with if you've got kind of white space at the end of lines of code or unnecessarily white space at the end of your file or between functions. There's a few other things around. So there's one here that deals specifically with NumPy code and applying best practices to NumPy. These typically don't come as standard when you install and use Rough, so you do have to put them into the config file. I've got links on how to do this, but essentially you list all the rules you want. And then you can also either extend to specific rules by specifying an exact rule number, and you can also ignore some rules if you don't want to apply them to your code. So a common one I see in scientific code is there's a rule that says you shouldn't be passing more than, I think, 5 arguments to a function. The reality is in a lot of scientific codes, we want to use more than 5 inputs, and it does make sense. So I often disable that rule if it makes sense in the particular context. So for subsequent exercises, we are going to edit this slightly. So we are going to add in the D rule here, which is going to give us some checks on writing our documentation. Because we've pulled in the entire rule set of D, we no longer need to extend it to include D202. So I will get rid of that. But we do now want D417, which is checking for missing arguments in a function. So we saw previously, if you provided an argument to a function that's not used, it will call it out. This will also check your documentation to see if you've missed out any arguments from your documentation. And then down at the bottom, we're going to stop ignoring the rules that we previously were here, so that we pick up a few more things as we move forward. So that's summarized there. Any questions before we move on? Super. So that's kind of the end of, yeah.
So just to check, Rough you integrate into VS Code, so that basically gives you corrections automatically, yes?
It will, so it will not automatically change your code, but it will give you kind of squiggly underlines or an indicator to say that it doesn't approve of that in real time, as you're writing. So it should work alongside as just as another plugin. Copilot, you can, so if you add to prompts for Copilot to try and make your code PEP 8 compliant, it's not bad now at doing that. Sometimes it's not completely correct, but in VS Code it would function as a different plugin, so you don't have to worry about that conflict. Okay, so we've gone through kind of the section on tooling, which is showing you things in your everyday workflow that you can make things better without too much effort. I'm now going to move to slightly more, I'm loath to say contentious, but maybe more slightly opinion-based things. but sort of things that at least to bear in mind whilst you're writing code that will hopefully lead to some improvements. So the first one is kind of clarity of when you're naming things in your code. So I think there's this sort of common phrase, which is that code is read far more often than it's run. And it's important, I think there's two things in here. One is that if you're sharing this code with other people, you want them to be able to understand it and use it properly. But you also want you to be able to understand it and read it properly. So I'm sure many of us have had instances where we sort of write some code, don't touch it for 6 months, come back again and look at it and sort of think, what on earth was I doing? How on earth did this function work? What on earth's going on? So there's a few things we can do to kind of work to make our code what's called self-documenting, which is to say we can improve the way things are named, the way things are structured, so that when someone comes and reads it, sort of we are not code readers, we are language readers. We can try and do some things to make it more clear. And this is particularly sort of pertinent these days. We're no longer restricted to 77 lines of Fortran. You don't need to name your variables A, B, C, and D. You can give them sort of something slightly more meaningful. So, like I say, there's no opinionated rules we can now apply here. It is much more sort of just things to bear in mind, but here are some things to think about. So the first one is thinking about the intention of the things you name. So sort of how would you read it, but also how would someone else who's seeing this for the first time, how would they read and understand the name of a variable? The second one is to sort of use consistent but readable names. So as tempting as it is to kind of abbreviate things and put them in as few lines as possible, you're not charged by the character. You're not paid by the character. No, that's the other one. You're not charged by the character, so you can use more than one. So whilst MS might make sense as mass in the moment, if you come back to this, you'll sort of look and say, well, is this meters per second? Is this meter seconds? What on earth was I meaning? So yeah, try to avoid abbreviations and single letters unless they're very common. If you're working in a field where there is a common abbreviation, particularly of maybe a really, really, really long term, if it's commonly recognized, yeah, make a sensible judgment, but try and avoid things sort of just for your own measure. Also trying to employ kind of consistency. So often people, if you've got something that will fetch a data set, people will call something like get data. If you've got multiple functions that are doing this, don't have get data, fetch data, retrieve data in your code. Try and become consistent throughout. So if everything's getting data, make sure everything is get data. It's going to make it a lot easier when you're then searching your code for different functions that are doing the same sort of thing. And then finally, I think there's this sort of anti-pattern that people have is to attach data types to names. So people will name things something like, I guess the name down here of array or dogs array or age underscore int. This is largely unnecessary in a lot of code, I think, particularly things like Python. So try and avoid this. This one is slightly more to taste, but one thing that I would suggest taking away is the advice on Booleans. So don't sort of, if you've got a Boolean that checks for, a particular flag, so say you're processing a large stellar data set and you want to have a flag for is something in the Milky Way, don't name that flag Milky Way, name that flag in Milky Way or is in Milky Way. That way, when you're reading the code, you'll know that when that sort of variable name is being used in places throughout, it's clear to you what it's doing. So that's kind of that advice there. Okay, so the next thing is sort of explaining variables. This is very much kind of a Python thing. Sorry, no, I'll roll back on that and come back and say. So explaining variables, the idea is if there's some obscure code, then you could perhaps clarify some of the intent by introducing an intermediate variable. So here, this is a sort of a rather trivial example. We've got calculate bus fare, if age less than 14, return 3. However, if we add an explaining variable, we would have something that says is child. So we're doing a check for is someone a child. This is true if their age is less than 14. And then we check later on, if it's child, return the child fair. I understand, before anyone wants to point it out, that this is wholly unnecessary in this small example, but the idea is to keep it as a small example. You will find sort of in much bigger codes, if you're sort of defining something and then using something much, much further down, sometimes defining this intermediate variable is very useful. When I say this is a Python thing, I think if you're concerned about performance, then it may be that there are performance hits you get from creating intermediate variables. But if you're not, if this is not the bottleneck in your code, sometimes heading for readability can come ahead of that. So something to consider. So a better example of this would be, sort of a more realistic example would be here. So anyone got any idea what this does? Yes? Yes, it's a regex, but what pattern is it looking for? And why would we want to look for that? How about that? So yeah, here we've got sort of regex. You had 99 problems, now you had 100. By introducing that number that clarifies that this is a regex that matches a phone number, when we then use this in our code, it's clear what we're searching for. So this is a sort of less esoteric, more realistic use of this sort of thing. So something to bear in mind. Okay, and then the last one is magic numbers. So who's come across magic numbers before? Okay, cool. So magic numbers, when we're talking about code, are numbers as in raw floats or integers that appear throughout your code, sprinkled here and there, that have absolutely no meaning unless you wrote it and have the context. So this makes the reason we don't like this is it makes code hard to read and understand. It's also, as I'll come on to in a sec, hard to maintain and adapt things. But there's a few things we can do to sort this out. So one is a bit like we saw before, to use the explaining variable for a particular number. Another option is to make sort of numeric constants in our code rather than putting them directly in line. And the last one is sort of that sometimes it does make sense to do this, but we can make the code a bit more readable by using comments. So here is an example for handling magic numbers. On the left is the not so good, on the right is the better. And so magic numbers here, we're talking things like the 9.81 here is just coded literal, so it's gravity, we know that one. But we've got things elsewhere that might be less apparent. So down here we've got a 60, we've got a pi divided by 1800, sort of what's the 1800 doing there? On the right, we can see, so the first one is to encode things as a constant. So here, rather than typing the 9.81 literally into our code, we've enshrined it at the top as a constant. And that means that now, whenever we use it, we've got some variable name that calls us gravity. There's also another advantage to doing this, if anyone can spot it. Exactly. So we're modeling Pendula on Earth. If instead we wanted to model Pendula on Saturn, on the left-hand side, we would have had to go through, find every instance of 9.81 in our code, make sure it's changed. You're typing lots of things, so there's more chance of a clumsy press. Also, there's a chance that you might forget to update one. There's a bug. On the right-hand side, update it in one place. You know that it's going to be working. The second one here, so this is kind of introducing that intermediate variable. So the code here is performing a small angle check to make sure that our assumption on sort of the linear pendulum equations are valid. By enshrining that as small angle, it becomes a little bit clearer to us that we're doing the small angle check. And then finally here down at the bottom, we're converting frequency into beats per minute. There's not really much use to doing anything more complicated, but we can make our life easier sort of in the future by just clarifying what our number 60 is there. If you want a more realistic version of where this is useful, it's a really, really common thing in climate codes where we have you have precipitation over a area and a time, and you want to convert the flux of precipitation into a sort of water depth measurement. It's really, really, really common to do that units conversion just by multiplying by a magic number, which is, I think, is sort of like 64,000. And you find that people will encode this everywhere. If you know what it means, you know. But if you come across it the first time, you sort of think, what the hell is this 64,000? And where in my code at some point did those units change? Putting a comment in there would have just helped explain that to someone. Okay, cool. So exercise number 5 is working through the code to look at kind of some variable names that could be improved and updating them. And also going through looking for some magic numbers in there. And there should be sort of an example of each one of these in there somewhere. So the challenge is to see if you can find it. Again, in the interests of time, I will let you sort of do that and have a think yourselves. What I will do is do the magic side-by-side comparison of, it's going to be exercise 5 and compare that to exercise 6, and we can maybe just scroll through and have a look. So this first one here, if I can fit it on the screen, what have we done in this case? Yeah.
Name magic numbers, put them as constants.
Yeah, exactly. Yeah. This is yes. Sorry, this is not a taxing question. So here, this one. So this one is not a magic number. Sort of what have we achieved here, perhaps? Oh, okay. I did search for a long time. I was like, why are there three log things in there? Okay, thank you. I understand now. From my point of view, I was thinking sort of this is the log of G something, and sort of this becomes a very long name. There's a lot of possibility. Indeed, when I was trying to change things, I would type 2 Gs instead of 3. So we've made it slightly more readable here, as in it's rather than high and low, we've got upper and lower. That one's maybe a matter of taste, but we've also added some underscores in there, sort of to give us separation between the words and some readability. Yeah, here we go. So the low data sets. So I would do my due justice and say you had named all these functions very sensibly. I changed them into bad names, so just the names of the data set, but we've sort of applied this consistency of describing what that function does. It loads it from file, and we've sort of adopted that consistency across all of the variables that are loading data from data sets. Super. Are there any sort of questions around that? Yeah.
It's a minor point, but I noticed that in the example you showed before, you defined the variable for gravity only in uppercase. Does that reflect some best practice, or your
Super question. Yes. So in Python, the practice is that if you're going to use a constant, then you do it in all capitals. And you'll probably find that in your text editors, it will change sort of. Your text editors that have got sensible highlighting in will pick that up and make it a slightly different color, which is in a compiled language, you've probably got some protections on, such as defining a variable as a const or in Fortran as a constant. In Python, I think I'm correct in saying that that doesn't exist. So if you define something as a constant, you could change it later. And so sort of the protection in Python is make this all caps so that you sort of think twice about modifying it somewhere else in your code. But yeah, good question. Okay, so moving on. We've thought about kind of naming things in our code as making it sort of more understandable, more easier to follow, more sort of better at communication to the author and better to communicate to the reader, to communicate our intent. But we can go sort of beyond that, and this is where sort of we moved on to comments, and really the sort of the pinnacle of these things is what we call the doc strings. Comments is where perhaps the most opinion lies, and I am not going to give you sort of any definitive do this, don't do this. Commenting is very, very much to taste. So, as I say, sort of, yeah, programs are written for people to read and machines to execute. So it's going to be turned into assembly whatever you do, beeps and boops and X's, ones and zeros. You want the source code to make sense to someone else. It's always going to be translated into the same thing at the end of the day. However, there's sort of this comment that a bad comment is worse than no comment. So if you put something in that is misleading, or you put something in that becomes outdated and sort of doesn't get updated when you change the code, you can actually make it harder for someone to understand something than if that comment wasn't there at all. And then the final one that's sort of the corollary of this is that comments are lies waiting to happen. So a comment is something you put in as a statement there. When you update the code, you have to update the source code to make it do something different. You don't have to update the comment, and lots of people don't. So sort of the takeaway there is sort of, if you've got comments, you need to maintain them in exactly the same way as you do the code, and there is no way of checking that you've done this. So a few things to avoid. Try not to put dead code in there. So as we say, we're all using version control. We don't need to comment out our lines. If we want a line to come back at some point later, we can just go through our git commit history. This is perfectly acceptable if you're iterating. So here, clearly we've been iterating over what particular variables we want to plot and what color and what markers we want them to look like. Sure, we comment out things as we're quickly iterating. If you're going to then commit this to git history, clean it up, don't leave this floating around. It leaves sort of multiple lines to filter through to work out what code is actually being executed. Second one, you wouldn't believe how many people put in self-explanatory comments, sort of set force or define acceleration. If it's obvious from the code that you've written, especially if we'd used maybe non-one-letter variable names here, then try and get that information into the source code itself, where you're forced to maintain it rather than in a comment. And finally, just don't put something, don't walk away from here thinking, I need to put lots of comments in my code, this is going to make it much better and much better software engineering. Don't put in redundant things. If you're incrementing a variable, don't tell me you're incrementing a variable. We've all done some kind of coding, we know that that's what that's doing. A few thoughts, don't duplicate the code, which I guess is sort of what we're saying here, don't say what you can already see. Also, writing a comment does not excuse you from writing bad code. I got this from Stack Overflow, I don't understand what it does, but it works. Yeah, I've written some code with that. But the premise, it's not an excuse to try and write a comment to explain away what you've been done. If it really is so obscure, there's probably a better way of writing this to communicate. So a good use of comments, I realize I've been saying, don't do all of these things. A good use of comments is to explain unidiomatic code. So an example of this that I did have was, there was a code I was working on that processed some satellite data, and I had a very clear loop that would process this data in the correct format, do all the relevant things, and it was really slow. It turned out I could do it in one line of NumPy, but it was a really, really long line of NumPy that was completely unintelligible. What I did do in that case was actually keep that kind of, keep that loop above it to say, this one-liner in NumPy looks very confusing, but here is what it's doing, and you can sort of look at this to then piece together how this works. Question? Oh, no, okay, so the other thing is, yeah, if you are copying some code, if you can provide a link to that source, so if you've pulled it off Stack Overflow, give the link to the Stack Overflow so someone could go and look at the context, at least look at the context from which it was obtained. And also just sort of any external references if they're going to be useful in there somewhere. Right. My final point on that, however, is that you shouldn't be documenting all the fine details of your code into comments. So sort of don't assume that anyone running your code will read the comments. The comments are there for if someone comes along to modify and understand your code. If you want to teach someone or communicate to someone how they should be using your code, this is what documentation is for. The comments are read by developers. The documentation that will be read by your users is for putting in doc strings. So how are people familiar with doc strings in Python? Okay, people have at least come across the concept. So these are sort of special strings denoted with 3 quotes that come at the start of things. So modules, files, functions, classes, whatever. And as with all best practices in Python, there is a pep for this that sort of tells us what they should say. So we can have a look here. Pep 257 gives us sort of this underlying thing of what should the doc string say, what should it be communicating. However, the important point to note is that it doesn't tell us how the doc strings should be saying anything. So it just tells us what should be there. It doesn't sort of tell us what the format looks like. The distinction I said, sort of comments are for how things work, doc strings are for how to use it. So PEP 257 doesn't tell us how these should look like, so we have to rely on other kind of guidance for this. As with everything, you've got a few options. So there's sort of the 3 big conventions out there are NumPy, Google, and restructured text, which is REST. The exercises that I've got here are going to follow NumPy doc. This is, I would say, the most kind of commonly used in scientific code. So NumPy is the convention that NumPy follows, also SciPy, also I think Matplotlib. So it's kind of the commonly adopted sort of research code approach. There is sort of full guidance on how to do this on NumPy doc. So if we go down a little bit, it will tell you all of the different things you've got. So the most common one we're probably going to be looking at is documenting functions. Is there one for functions? Let me disappear. Yeah, okay. So it describes as kind of all the various things that we could have. So the main thing you should have is a short summary of your function. You can also have extended summaries. You should be documenting all the parameters that go into your function. You should be documenting the things that your function returns. Few other things in here we can talk about. There's a section sort of in the standardized doc strings for providing references to sort of where this code has originated, and also for providing examples of how to use it, which we can come back to in a moment. So an example of this, and this is sort of what I would encourage you to do for your functions as a bare minimum, is to have a short one-line description, a list of the inputs and outputs. There we go. So, did I Yeah, so the short one-line description, the idea is that anyone coming to your code can read this, can immediately see what this chunk of code is doing. Don't make it pages and pages and pages. Make it so that someone can read it and immediately digest it. The second one is a list of the parameters that go in. So here you should describe them with the name of the variable as it goes into the function. You should then also document the type of that variable that's expected for that function. This is sort of to help people not avoid misusing your code. And then finally, you should give it some description of what that parameter is. So, I don't know, what is that variable coming in? Gravity? Is it luminosity? I don't know. And the exact same principle applies for the return statements. But you separate these out so there's sort of the inputs and the outputs as two separate points. Things that you can also consider are an extended summary. So after the there we go. So after the one-line description, you could have a much a longer description if you feel that you need to provide additional clarity, but preserve that one-liner and then follow it up. You can also give documentation for any errors that your function might raise, so that people can be expecting this and know how to use appropriately. And you can also give, as we said, examples of usage and some key references. So here is an example of some of those things, a more realistic example. So this is an equation from some of my old code where we're calculating the gyro radius of a particle around a magnetic field line. And there we go, short one-line description tells us what it does. After that, we've got the variables that are coming in. So we've got all of them. We know what sort of thing we're meant to be providing. Particularly useful for scientific code as well is providing some units in there. So when I was working in sort of the radiation belt stuff, they have this horrible habit of providing energies in electron volts and not being sort of specific about which functions are using electron volts, which functions are using megajoules. So that's something useful to stick in here. Make sure people are using your function correctly. We've got a description of what it's sending back out. And then the other nice thing is there's this option to put sort of citations in. So if you've coded up an equation from a paper or an equation from a textbook, you can actually provide a citation back to that as is done here. There is also the option within some sort of documentation engines to embed LaTeX into this. So if you want to kind of actually code in a LaTeX equation that someone can look at when it renders, you can do so. Cool. So again, how do you remember how to do all this? How do you make sure that you're compliant to best practices? The answer is that we use more static analysis tools. We use something to shout at us if we're not doing it. So this is what we call PyDoc style. So PyDoc style is kind of an engine that enforces these rules, and again, it's embedded into Rough, so it's all within that one tool we've already installed. And much like we ran the static analysis that went over our code and pointed out where bits and pieces were missing, this will run over our documentation in all of the doc strings and point out to us where bits and pieces are missing. So, yeah, if we ran this on the code that we've got here, sort of the feedback that we'd have got is that we're missing an argument description for B. So you can see up here we've got B for the magnetic field, but we've actually left this out of the list here. It's going to shout at us and tell us to put that in. Other things it's sort of got with formatting, so telling us where blank lines and other things should be. And the other interesting one I find it catches sometimes is more stylistic, telling you to sort of write things in imperative statements. And we mentioned before when we were updating the configuration that by default, Rough won't catch when you've forgotten a variable from here, because it could be that there's a reason for doing so. But we extended to add a rule to do that in our config file, if you recall. So are there other questions on that before I move on? I feel there's quite a lot and I talked a lot. So I would, yeah.
I guess maybe a general question around this, like
Right, yes. So this is boring to do, and if you've got a code that you're writing, it's not too much work to put these in as you write it. If you want to go back to your code and implement this now, it's boring. And this is a tool that large language models are good at doing. So you can point it at a file, tell it to generate the doc strings. So a few things to note are you want to tell it to generate doc strings in the NumPy. If you want them in the NumPy format, tell it that you want them in the NumPy format. Also, if you want these additional things like sort of any description of errors or description of warnings, add that to your prompt and ask it to do that. And finally, as with use of LLMs in all of coding, read it after it's generated, just check that it is doing the right thing. Some of the help with that will come from using sort of the rough checker to check those doc strings, but do just read it and make sure it makes sense to you. Make sure that it's interpreted your variable, that is, I don't know, GRV, make sure it has interpreted that as gravity and not generalized radiative forcing from the atmosphere. Cool. So yeah, again, other languages have their own sort of thing. If you're working in Fortran, you've got Ford is kind of the common thing. Here you sort of use the double exclamation marks and put descriptions after the subroutine, and then you add sort of the descriptions at the end of the line like this. C++, the common sort of approach, and also C, the common approach is to use Doxygen. So here you've got kind of, you label your parameters and your return variables, you give them the name and you give them what they are doing. Julia sort of builds on Python with this sort of common docstring format. R has sort of their version of Doxygen, but it's R, so everything has to have an R in it. And the real, so the real power of this that we don't have time to touch on today is that whilst this is really useful for when you're reading your source code, if you followed this standardized format, then there are lots and lots of tools out there that will turn these sort of standardized formats in your code into online documentation. So if you've ever been to, I'm trying, where can I go find? Here is one I prepared earlier. If you've ever been to sort of a read the docs page like this, and you find, here's the definition of a class. Oh, look, it's telling me what the input parameters are. It's giving me a nice description of this, all of this sort of stuff. This has all been automatically generated from these doc strings here. So we've got sort of detect nose parameters, stitch nose parameters are the inputs to this function, designated as attributes. When we've run this sort of docstring generation thing on them, they've come out into all of this really nice documentation. So if you are looking maybe later in a project at producing some good online documentation for your code, either because you're making it public or just sort of internally for usage, there's a lot of tools that will build on top of using this default docstring layout to do this. Cool. So exercise 6, again, I will let you do sort of in your own time. The exercise is to work through the code, have a look for removing sort of bad comments, dead code, and updating some of the doc strings as well. So you might want to have a go at using LLM, particularly seeing as it's your code, see how well it matches what you were writing. And as I say, if at any point you're unsure about anything that's going on, you can look at the starting point in exercise 7, gives you the solution for that. Cool. Okay. How are we? Okay, we're not bad. So I think we're on the home stretch. I've got a little bit about structuring code. Hopefully a lot of people are kind of aware or familiar with some of these things already. I'm probably preaching to the converted, but the biggest sort of bad smell, so bad smelling code is a term that people use to sort of say when you look at the code, you sort of look at it and think, oh, that's a bit off. Sort of one of the worst smells in code is when you see a lot of duplicated code. As we've already covered sort of with those using constants, this is a bad thing because you will forget to update everything. So again, sort of drawing from anecdotally, there was a code I was working on the other day where we'd been trying to update and use some new functions, but make sure that we hadn't changed the overall results of the researcher's analysis. And this worked in sort of 5 out of 6 notebooks, and the 6th notebook just wouldn't work correctly. In the end, what we boiled it down to was they'd found a bug in one of their notebooks. So they had kind of a search loop, and the termination condition had been, they'd caught it somewhere, they'd updated it across 5 of those notebooks, they'd forgotten to update it in the 6th one, which is why things were now not working. The solution to that was to actually, rather than copying and pasting that code across every notebook, this is now a bad smell, you should not be doing it, pull that code out into one single point of truth, say a function, a call, and then use that in each of your notebooks. Other things you should sort of be thinking about here is the readability. Rather than having sort of chunks of one huge, super long chunks of code, if you can break up things into functions, it makes things much more readable. So rather than having 60 lines, if you can condense this into sort of read data set, or sort of a call to a function to read the data set, a call to the function to clean the data set, a call to the function to convert the data set to the format you want, a call to the function to plot that data set. That's a lot more readable, and you can then chase down the relevant bits you want to work on, rather than just having this giant sort of behemoth. And then again, sort of this pays its dividends when you're trying to extend your code or do other things. You can then use these as sort of building blocks. So if you have been using a Poisson solver and you decide now you want to try out using a different solver, if you've got a function that implements that Poisson solver, it's easy to write a different solver, say Gauss Seidel, and bring that into your code rather than having to edit it somewhere in the middle of the source. Yeah, again, I think there's sort of an example here. You can see we've got this various repeated code. Again, it's sort of a fairly esoteric, simple example. We've got repeated calls to sort of L cos theta or G cos theta. The nice thing to do is sort of clean this up and make a function that's going to carry out this operation in one place, and then use that function throughout the code instead. Sort of going beyond kind of single files where you're breaking things up into functions, if you start looking at Python packaging, which is what we mentioned at the start of the session, you can actually look at breaking these things into modules. So in NumPy, if you import NumPy, you can then import numpy.random, numpy.interp. These are all separate modules, and the idea is that that code is compartmentalized into one place, keeping it tidy, preventing it from getting too long. You can do exactly the same things in your code, following sort of packaging concepts. So there's an exercise that doesn't deal with sort of the Astro code, it's just a plotting code, and it's sort of looking at adapting this to try and make it more legible. But does anyone have any questions on sort of those ideas? I think probably they're things that people understood already. What I would say is that try and avoid the sunk cost fallacy. If you did have some code that was written in a linear fashion, but you find yourself copying and pasting it perhaps more than once, it's worth the time investment at that point to refactor it out into a separate function or into a separate class for when you come across this problem, or come across trying to reuse it further times in future. Okay, so the last one is less of an exercise and more of a sort of teaching and listening. And we're talking about readmes, licensing, and other such files. So how many people's code has README? Oh, I was hoping there'd be more. Okay. How many people's code has a license? How many people's code have other files? READMEs are, the README is a file that usually is contained at the top level of a repository. If you've ever been to something on GitHub, it's the file that sort of gets generated on the homepage for that repository on GitHub. So if we go here, where you cloned the repository from, there's sort of all of this information down here. This is provided in this README file that sits at the top of the repository here. And so it is so ubiquitously known as the first point of contact that GitHub, but also GitLab, have chosen to make it that first point that you see when you go to a repository. And the idea of this is that it gives people sort of this essential information on what the software is, what you can do with it, and importantly, how to get started with something. So you might not be looking at making your code public at the moment, but sort of if you are looking at having a public tool from your research, people won't necessarily use the best tool for a job. People will use the easiest tool for a job. So if you can give good documentation and it's easy for them to start using something, that's probably the one they're going to pick. As always, sort of that's the base standard. If you want to move towards the gold standard, there's more things we can add. So you can give sort of some contact and some citation information. If it's a bigger project, you can give people some information on how they can contribute things that they might have done to extend this in their own research back. And you can also sort of tell people how they can sort of use your code and build upon it to do further research. So these days, typically, these are written in sort of markdown syntax, which is kind of a standard for writing documents to render things with nice headings. Historically, these would have just been a plain text file. If you write them in markdown, then you get sort of this nicely formatted thing with lists and headers and everything else. And yeah, if anyone's not familiar with markdown, the idea is you're just using sort of these delimiters to tell us we've got headers, lists, all of this sort of thing. So that's the syntax people tend to follow these days. And I've got a link to kind of the markdown guidance here. If you want to get started with this, there's a couple of useful websites. So either of these, I think, will take you somewhere, and it will, that one's sad, let's try the other one. Here we go. It'll give you sort of some automated tooling to click on what are the things you want to include, and then allow you to type them in here as they appear. So yeah, makes the process slightly easier if you're writing one from scratch. So yeah, being a bit more specific, sort of the essential content that needs to go in there is the name of your code, sort of the overview of what it does, information for someone on how to build it. So this comes right back to the start. Tell them where the list of dependencies are, perhaps in a requirements file. Tell them how they can install these, pip install. If it's sort of more complicated, you need maybe make or cmake. Give them the instructions for doing this. Make it as easy as possible for people to get going and started with your code. Additionally, sort of have some simple examples in there for people, and also maybe some basic documentation, or at least the pointer to where they can get a little bit more help. Other things that are nice to have is sort of if you've got a paper that's based off this work, provide a reference to your paper. Maybe a list of people who are using it, or a list of people who contributed to the work. There's a whole load of things that can go in. The only thing I would warn against is kind of don't make it too long. If you find that something's getting crazily huge, either put in a table of contents with some hyperlinks, or consider making some online documentation to accompany your code project. Cool. Any questions on READMEs? No. I'd say again, it's sort of incremental. Add one to your project with the bare minimum, and then update it sort of as you're going through. Cool. So the second one is licensing. So any code that is public should have a license attached. And this is to make it clear to anyone who might be using it what the conditions of that use are. So if you upload your code somewhere in this country, you retain the copyright, and so in theory, no one could use that. By attaching a license, you then begin to describe to people how they can use your code. So part of it is kind of protecting your ownership of that code, but it's also about limiting your liability. So if anyone's looked at licenses before, sort of the most famous statement that comes through all of them is, the code is provided as is, which sort of when you dig into the small text is sort of, here is the code, I've made it public, anything you do with it that causes a problem is your problem, not mine. So yeah, you should attach a license to your code. And the important thing to look at, which I've not got here, is that it should ideally be OSI approved. So the open source initiative kind of has these standardized licenses. Generally, I would suggest not trying to write your own license and not trying to modify a license. One of these is usually sufficient to cover you and is a sort of a better way to go. But the exact selection of what open source license may depend on both you and what you want to do with the code, but also on your funding as well. So there are some funders that have a preference for more permissive licenses or more open licenses, such as the MIT license. There are also funders who maybe have preferences for the more sort of hardcore open source or the copyleft licenses, such as the GPL licenses. And I'm happy to talk to people sort of more about this if they want to. The other thing to note is that GitHub and GitLab also contain sort of helper functions to allow you to create popular licenses. So I think if you have a repository on GitHub and you go to... Thank you. Thank you. Yes, add file. So if you go to create new file, you'll find that if you type license there, it will suddenly give you this extra pop-up. It's recognized you want to create a license in the standardized license format, which is a file at the top named license, all in capital letters, and it will let you sort of select from a template. So you can go here, you can say, oh, I want the MIT license or the GPL license. It gives you a little bit of information about what this has. And there's also this website here, Choose a License, which sort of gives you this choose your own adventure, choose your own license. If in doubt, I would say speak to some of the data managers in the library or in sort of the software bits of your organization who might be able to provide more guidance. Yes?
So if one takes a license or one amends an existing license, what exactly is the legal validity of that? As in, do licenses need to be registered somewhere, or if I write my own license that is legally binding by itself?
So if you write your own license and you put it with your code, that is the license that appears. What you want to be careful of then, really, the license is less about protecting your ownership. As I say, if you provided it without a license, at least here, and I'm not a lawyer, so I'm not 100% on what I'm saying, but you, by default, you have the copyright. What you're doing when you provide a license is you're telling people how they can use your code. And this is where you have to be a little bit careful, and it's a discussion we often have, is whether you choose a more permissive or a more, I'm not going to say restrictive, but sort of the correct term is copyleft. If you choose a license like the MIT license, you essentially say, here's my code, anyone can take this code and do anything with it. If you choose the GPL license, this is sort of what we call viral licenses, and it says that here's my code, it's available for you to use, but anything you do with it must also be GPL, must also provide this code, must also be made freely available. And so if you write your own license, it may not be immediately clear to people what they can do. Also, people are used to using these standard licenses. Like if I see an MIT license, I know what I can do with that code. If I see a GPL, I know what I can do. If I see your license, I'm probably not going to read it I'll just go and find something else. But yeah. So yeah, talked a little bit here, sort of you've got, public domain licenses, which are, here is my code, do with it what you want. On the other end, you've got sort of proprietary, which is sort of, here is my code, you can do nothing with it, possibly not even, here is my code to read, here is my code as a binary that you can run. And then you've sort of got things in the middle. So yeah, copyleft and permissive. You've got, copyleft is sort of, you've got to distribute any code that builds on this under the same license. More permissive is sort of saying, you can take this code and do with it what you want. You can build on top of it to make money. You can build on top of it and not release the source code. The one thing I would say, if you're using other codes under certain licenses as part of your code, you do want to just check that what you release your code under is compatible with that. But I also want to say this is sort of, I think people get much more worried about this than they should. There are people you can speak to for advice that will help you with this, and it shouldn't be something that stops you releasing your code or trying to collaborate with people. I think we've gone through that. Like I say, this is the MIT license, which is just one, and there's this sort of common statement, the software is provided as is, without warranty, we went through adding a license in GitHub. There's a similar tool in GitLab if you're using, say, the university GitLab, or your group uses GitLab. Similar tool there that you can use. Cool. So finishing up with that bit is sort of other potential files. The README and the license, I would say, are the essentials. Other things, you can have descriptions of sort of how people should contribute to your code if they want to sort of contribute improvements they've made. A reason for doing this, there's an amazing atmospheric simulation code that if you go to the European Geosciences code in convection, there will be 20 different research groups presenting, all of which 80%-ish will be using the same atmospheric model, or so you would think. The problem is that this atmospheric model is only available by asking the author nicely, and so lots of different researchers have done this. They, in their research groups, have then all implemented their own improvements, their own bits of science. Some people look at boundary layers, some people look at radiation. The problem is that these are all then siloed. So really good radiation is only available in this one, really good precipitation is only available over here, and any bug fixes that go into the original code are never being picked up and propagated back. So this is sort of a good reason for contributing back to these codes as well. If you've got papers, you can add a file to your GitHub repository that tells people how to cite it if you're using that code. So if we pull up here, there is, if you include this citation.cff file, you'll see that GitHub again recognizes this and will actually give you a nice little thing saying, here's how you can cite this work if you've been using this code. So that's another nice thing to include if you've got a publication. And yeah, other things that you can look at. A few more things that went beyond the scope of today. So like I said, packaging, sort of building on documentation to actually get nice online stuff. Also some stuff with type hinting, so sort of providing a bit more security beyond the duck typing that we talked about earlier. There are some references, and there should be another. No, I skipped over it. Hang on, why did we? Okay, cool. So hopefully some of these things have been interesting. It's been a fairly whistle-stop tour. So if you need more help with this, you can get in touch with your friendly neighborhood RSE, Gajit. And there's also the university RSE team who can support researchers with sort of some of these aspects. And there's regular clinics that I think you're also part of. So if you're using the HPC CSD3, you should be on the mailing list, and these are advertised periodically there. If not, speak to Gajit, but there's sort of, I think, almost monthly-ish clinics over at the West Hub to sort of sit down with your code and look at improving it or solving problems. A few other examples here. So there's lots of links dispersed throughout. There's also a really nice kind of webinar, I think YouTube video here, so check that out if you want perhaps a bit of a longer description. There's also training materials, so Universe HPC, and also the carpentries provide a lot of software training that's really nice as well. And with that are the references in the end. And if anyone has any more generic questions about this sort of thing, I'm happy to chat now. Or not. It is Friday afternoon.
If you guys want to thank Jack for the session.